Okay, one more example of composition of function. In this case, we are given the two rational functions of x over x minus 1 and g of x equal 1 over x plus 2. Every time I see rational functions, what I like to do is I like to see if I can factor them out. Well, we cannot factor out both of these functions anyway, so we are going to go ahead and find the domain of the function f and then the domain of the function g. Now to find the domain function f, take the denominator, set it not equal to 0, and then you solve for x. So that's going to give us x cannot be equal to positive 1. For the function g, the domain can be found by taking the denominator x plus 2 and set it not equal to 0. So this will give us x cannot be equal to negative 2. So these are the two restrictions of both these functions. So what is f composite g in terms of x, which is f of g of x? Well, function g is here. You're going to take this function g and replace all of the x of the function f. So we are going to have, instead of x, we are going to have 1 over x plus 2. Then all of this is divided by another 1 over x plus 2, and then minus 1. Now 1 by itself is the same as 1 over 1. So finding the common denominator, I realize that the lowest common denominator for both of these is x plus 2. So if I just multiply this denominator by x plus 2 and doing the same thing for the numerator, I'm going to have the same numerator, x plus 2, 1 over x plus 2, but the denominator is now going to be 1 over x plus 2 minus parentheses x plus 2 over x plus 2. Now, with the common denominators in the overall denominator, I'm going to have 1 minus parentheses x plus 2 all over x plus 2. Simplifying a little more by recognizing the fact that there's the invisible negative 1 on the front here. So distributing this invisible negative 1 into the x plus 2, I'm going to have 1 over x plus 2 over 1 minus x and minus 2 all over x plus 2. But combining like terms with 1 and a minus 2, I'm going to have still 1 over x plus 2 all over negative x minus 1 and then over x plus 2. Now over here we have a fraction divided by another fraction, so switch this division into multiplication by keeping the fraction in the numerator, 1 over x plus 2. Change it to multiplication, and we are multiplying by the reciprocal of the denominator fraction. So we flip this, which will become x plus 2 over negative x minus 1. And we can simplify it out a little more by recognizing the fact that we have a common term x plus 2 right here and right here. So this step, the restriction is going to be a removable discontinuity, where we get to take x plus 2 and we set it not equal to 0, and that's going to give us x cannot be equal to negative 2. So that's one restriction. Another restriction is this one right here. Negative x minus 1 cannot be equal to 0. Add x to both sides. We are going to have negative 1 cannot be equal to x. So that's the second restriction at this step. So that means we are going to have 1 over negative x minus 1. And of course, the restriction here at the result is that same thing right here. X cannot be equal to negative 1. Now, what is the domain of this? Well, before we can find the domain of the entire composition of function, what we want to do is that just like in the last step, which is a result, and in the second last step right here, we want to find all of the restriction of every step of the way, because we want to make sure that all of the fraction that we are dealing with cannot be undefined. And the way we say that a rational function cannot be undefined is by excluding a few specific x values that would make any one of these denominator become 0 should we end up having to plug in that specific x value. So let's go back to the first step. First step here, we have this denominator, x cannot be equal to -2. And oops, not this one. And this one right here, x cannot be equal to -2. Yeah, that's -2, my bad. And even this step right here, same thing, x cannot be equal to -2. And of course, this x cannot be equal to -2. And x cannot be equal to -2. Same thing can be said for this step. X cannot be equal to -2. Oops, wait, not this, but this. X cannot be equal to -2. Yeah, that's -2. And this one right here, same thing. Right. So x cannot be equal to -2, x cannot be equal to -2 at this step. And same thing for this step. X cannot be equal to -2, and this right here, x cannot be equal to -2. So looking at all of the steps, we see that all of the restrictions in every step is x cannot be equal to -2 and x cannot be equal to -1. So that is all of the restrictions of all of the steps. Now, what about the inner function that we plug in, g of x? Well, the domain of g of x has a restriction of x cannot be equal to -2. So taking into consideration of all of the restrictions of the result, every step, and the inner function, all of our restrictions are actually only x cannot be equal to -1 and x cannot be equal to -2. So the domain is all real numbers except x cannot be equal to -2, comma, -1. So on interval notation, for interval notation, we look at the number line from -infinity to positive infinity. Let's just say -2 is here and -1 is here. We are excluding these two values, so we put an open circle. Always going from left to right on a number line. We're going from -infinity up to -2, but not including -2. So this part that I'm shading, and always at the parentheses at the infinity, and we are excluding -2, so we are putting the parentheses. We are jumping to the next part, which is between -2 and -1, so we are supposed to put the union sign, and then still excluding -2 up to -1, but not including it. This is the interval notation for the middle part. Jumping to the next part, we have to put another union sign, and we are still going from excluding -1, but all the way to positive infinity. And this is the interval notation for the domain of f of g of x.